Okay, space-time. So here's the idea. The idea is we can travel through time, we can travel through space, but typically when we're traveling through space, time is passing. And we have this interaction here of traveling through space and time, okay? Which is pretty typical. But let's think through this. If we're going to stand still, we're not traveling through space at all, right? We're not moving the X direction, Y direction, or Z direction, but time is still passing, okay? So this would be like represented at the origin here. I'm stationary. I'm not moving with any velocity anywhere. And so then my travel is all through time, and it's not through space, okay? And here's the idea, is that this is where time is passing like we perceive it, okay? And then this graph shows us that as we take a component of this vector to not just be time, but we're going to give a component of that to be space, it's going to take away from the time component. And so it's like we're slowing down, okay? We'll talk about what we mean here in a moment with time dilation, but the main idea that I'm trying to get to is that as we increase our velocity traveling through space, that has to be compensated by a loss of our time vector, so that our overall resultant remains the same. This is going to be our constant value. Okay, this is why the speed of light is constant. Okay, so we're going to have this constant space-time vector. And if we take away or add to one component, it will take away from the other. So if I'm approaching the speed of light traveling through space, let's say I'm going half the speed of light now, to get to that point that I'm traveling at half the speed of light, then we're losing a time component. And we can get to a point where we're traveling all through space and not through time. And so then that would mean you're no longer traveling through time and only through space. Time does not exist when you travel at the speed of light, since light is what we measure time by. So traveling from one place to another at the speed of light would literally take no time at all. So it's all about the perception of what's happening. That to the person traveling the speed of light, it would seem like no time has passed, but to the person observing that person traveling at that speed, it would appear as if they've stopped. Okay, let's continue. This is called time dilation, okay? So let's assume we have a moving light clock, okay? Meaning that we're going to have, let's see, a light, a photon that's emitted here, right at like a mirror. And then this photon's going to bounce back and forth between these mirrors, okay? And this is a great way of measuring time because light travels at a constant velocity. And so as those oscillations back and forth occur, we can know how much time has passed, okay? But then we get in this really interesting situation where what if we're observing two different inertial reference frames? That the person, let's say inside the spaceship, inside the rocket, sitting there watching this, the light's bouncing back and forth, right? But then for someone outside of the spaceship, watching the spaceship travel through space as well, we see the light going a greater distance if this speed continues. Okay? The greater this velocity becomes, the greater that distance that the light will have traveled. Very similar to, where did I set that down? Very similar to this. That Ted perceives the ball going up and back down, but Alice sees it making this parabolic motion. So what if we had a light photon bouncing back and forth? Ted just sees it bouncing forth, but what Alice sees is a zigzag. It's going and bouncing and going and bouncing, right? But how could this be possible if the light is traveling at the same speed in both reference frames? That it's going up and back, right? The photon's going to hit the mirror and go back. And then same thing here, it's going to hit the mirror and go back. And Alice perceives it traveling a greater distance, and Ted perceives it traveling a shorter distance, but the speed is constant. So the time component must be what's changing then if the speed's not changing. Okay, let's derive this. Honestly, it's really quite simple. We're going to use Pythagorean theorem to help us with this, okay? So, we have this distance traveled, right? But then we also can make the argument that the other person saw the light travel this distance. So, we have the light traveling this distance and the light traveling that distance. Now, first, there's a couple ways we can write distance, right? We can represent it in meters, or we could say that a distance is equal to a velocity multiplied by time. We need to be okay with this. Let's see, distance in meters. A velocity is meters per second multiplied by time, which is seconds. And so that would cancel and just leave us with meters. So I'm going to represent this distance that the object traveled as the speed of light, that velocity, multiplied by that time observed by the person outside of the rocket ship. And now inside the rocket ship, we have the light traveling this far. And so that would be the speed of light multiplied by the time it took for that person inside the rocket ship. So I'm just going to distinguish the two different times as t and t naught. Okay, so the t naught being the time observed by the person traveling with the velocity. Okay. All right. Looks like we have a triangle. Oh, look, there's another component here. That would be the distance traveled by the object and the amount of time observed by the person outside the rocket ship, right? So this would be velocity of the object multiplied by that same amount of time. Okay. We have a right angle, velocity of the object multiplied by time, velocity of light multiplied by that same amount of time. That took the same amount of time for the light to go from here to there as for the object to go from here to there. And then for the person inside the spaceship observing light traveling this far in a certain amount of time. Okay. Let's do a squared plus b squared equals c squared. Okay, our Pythagorean theorem here. So if we take this will be our c squared, and that will equal a squared plus b squared. And I want to solve for this time viewed by the person outside of the spaceship. What's happening there, okay? So the first thing I'm going to do is if I'm solving for this, I want to get the two variables, identical variables, on the same side of the equation. So I'm going to subtract this component because it's added to the other side. Okay. And so now what I can do is divide by the speed of light, and so that would have it cancel on this component. Okay, I'll show you what I mean. Okay, so it can cancel here, but then it still has a component there, right? So this would be t squared minus v squared t squared divided by c squared equals t naught. And now that I've done that, I'm going to factor out the t's. So this would be t squared multiplied by 1 minus v squared c squared, right? If I multiply t squared by 1, that would be t squared minus multiplying t squared by this fraction would be v. Oh, trying to show you this comparison. Oh, sorry. So I'm going to multiply t squared in just to show how I factored this. So this would be the same, multiplied by 1 would be t squared minus, and then this fraction multiplied by t squared would be v squared multiplied by t squared divided by c squared. Okay, and that equals t naught squared. Okay, now that I've been able to factor this out, I'm going to solve for it. So I'm going to divide by this component because it's multiplied to t. So t squared is equal to t naught squared divided by 1 minus b squared over c squared. Wonderful. And then I'm not solving for t squared, I'm solving for t. So I'm going to take the square root of both sides. So that would be t is equal to t naught squared divided by what's on our denominator. Now, if you take the square root of a fraction, that's the same thing as the square root of the top divided by the square root of the bottom. And t naught squared, square root, would just be t naught. So what our final equation is, our time dilation, t is going to equal t naught divided by the square root of 1 minus v squared over c squared. Okay? Now, if the velocity of the object is really, really small compared to the speed of light, we can make this assumption that it's practically 0, right? And so then we would have 1 minus 0 would be 1. The square root of 1 is 1, and so then t naught over 1 would just equal t. That this observation of time dilation when this is really small compared to the speed of